Alright, so this is day 31, second video. We were doing a simulation just to see if our observed counts, if we just randomly generated some observed counts, okay, some observed counts. So we've got our observed counts, we've got our colors, blue, orange, green, yellow, red, and brown out of total. Out of 50. And then we have our expected counts that we've already calculated on the previous page. So I've got my sample here, and I've already found that I observed 16 blue, and then if I go down to 44 and stop there and count, so 31 minus 16, that's 15 orange. So then we go to the number 60, right there, that's 37 minus 31, so that's only 6 were green, and then yellow would be 61 to 74, 1, 2, 3, 4, so 4, and then 75 to 87, so 1, 2, 3, 4, 5, 5 red, and then 88 to 100, 91, 1, 2, 3, 4, 4, so 4 of them were brown. And our expected counts from the previous page were 12, 10, 8, 7, 6.5, and 6.5 out of 50. So if we were to do a chi-square test for this, we'll do the same calculation. Our chi-square test statistic is the sum of every observed value minus the expected value squared, and then divided by the expected count. So we're going to the sum of every observed minus expected squared divided by the expected. You'd be expected to write that formula down. And now I'm just going to calculate these. So I did the calculation, and what we get is 6.927, which is quite different than the last one that we got. So the higher the chi-square value, the more different our observed values are from our expected values. So we could make whatever kind of conclusion we would want there. In this case, how high do we need to go? That will be the question. So let's continue talking about the chi-square test, and we have a new distribution. So to find the p-value without a simulation, we would have to use the chi-square distribution to approximate the sampling distribution of that value. So we would have our chi-square value, we'll use the one from our random sample, the chi-squared of 6.927. So now what we need is the probability of getting that chi-squared value. The probability of getting a chi-squared that large, assuming that the distribution of M&Ms is as the company says. So the t-distribution, the chi-square distributions are continuous and determined by degrees of freedom. So degrees of freedom here is the number of categories minus 1. So that's the formula. It's right down here. So the degrees of freedom is the number of categories, not including the total, minus 1. So in our problem, we have 1, 2, 3, 4, 5, 6 categories. So our degrees of freedom would be 6 minus 1, or we would have 5 degrees of freedom in this case. Now the chi-square distribution is also in the back of your book. And if you look at your distributions in the back of your book, I'm just going to pull the back of your book up here right now. The chi-square distribution, let's see, maybe I won't even be able to find it. There it is. It is in the very back of your book, and this is the chi-squared table. We've got our degrees of freedom along here, and then we have our significance levels, 10%, 5%, 2.5%, 1%, 0.005. So we've got chi-squared is a little bit different. It's only for positive values, and if you think about it, categorical data counts can only be positive values. We aren't going to have anything negative, or we're not going to have things on either side. The chi-square statistic just keeps getting bigger and bigger. And we would like to know the probability. It's the right tail probability. So the probability of getting an observed value as high or higher. That is always the case with chi-squared, as high or higher than the observed. So that's in the back of your book. So So I want to double check, do we have the right number of categories? So we did have the right number of categories. 1, 2, 3, 4, 5, 6 categories. So, okay, so the chi-square distribution just happens to look a little different for each degree of freedom. It's just the peak, they call it, the peak. Now, if degrees of freedom is 1 degree of freedom, then it kind of looks like this. If degrees of freedom is 5, it looks like this, 10. The higher the degrees of freedom you have, the more flattened out, I guess, it starts to look. So the mean of a chi-square distribution, the balancing point, is equal to the degrees of freedom and the peak. So the mean is equal to the degrees of freedom. So 5 degrees of freedom would mean the mean of our chi-squared with 5 degrees of freedom is at 5. The peak, this highest point, is 2 below the degrees of freedom. So here would be 5, this would be at 3. Okay, 10, here would be 10 would be the mean, and 2 below that at 8 would be the peak. All right, so if we want to find p-values, so we want to find the p-value, what's the probability that we got a chi-squared value greater than 6.927? So, and a little explanation on degrees of freedom. So what are degrees of freedom? Consider a blank table, okay, a blank table with 6 categories and a total, okay, so we have 6 categories. So 1, 2, 3, 4, 5, 6, and then we have our total. So we have 6 categories and we have a total of 250, let's just say. Here's kind of the idea behind degrees of freedom. So how many cells do you need to know in order to fill out the entire table? So, I mean, if I don't know anything about the table at all, I would have to know all 5 of those before I could fill in anything else. If I knew these 5, then I could add them up and subtract from 250 to get the 6th. But if I knew any less, that wouldn't be good enough to fill out the whole table. So that's kind of how the degrees of freedom works with the chi-squared. How many categories do you need to fill in order to be able to finish filling it in on your own? All right, so we are going to find the probability that our chi-squared is greater than 6.927, and the chi-square tests are always greater than our chi-square calculation. So we've got using the table, so our degrees of freedom is 5, and we would want to pick an alpha level, so we'll pick an alpha level of 0.05. So we go to our table, and at 5 degrees of freedom, well, this is actually the chi-squared, just finding the chi-squared number. So I guess we won't even use that table. So it's much easier if we just use our calculator. So using the calculator, there's a chi-squared test in the test menu. So we're going to go to stat. So this is how to do the chi-squared test on your calculator. Go to stat, go over to tests, and you're looking for the chi-squared test. Now you're going to see a few of them, and I want you to pay attention. We are just going to do the chi-squared test. I know this says chi-squared GOF, goodness of fit test. No, we're not ever going to use that one. So this is just the chi-squared test. It's the first one. Okay, so I'm going to hit enter on that. And can't use this test though. So back up, sorry. This is for later because we'd have to put these into matrices, and we don't really have a matrix that we can use here. So back up, erase that. So actually we need to go to second distribution. They have a chi-squared CDF. Okay, that's what we need to use here. So chi-squared, not PDF, chi-squared CDF. And then you would want to put the observed and then the expected. Something's wrong. I probably just want to go to second distribution Oh, I was still in the test menu. Okay, here we go. Now, the lower bound is always the chi-squared value, so chi-squared CDF, then you're going to type in your lower bound, which is always your chi-square statistic, 6.927. And then your upper bound is going to be infinity, a bunch of 9s. Then your degrees of freedom is going to be 5, or whatever you have, and then hit enter. So 6.927. The upper is 999, degrees of freedom is 5, and then I get my p-value. The probability that chi-squared is greater than 6.927 is equal to 0.2261, okay? So then you're going to compare that p-value, probability is a p-value, to alpha of 0.05, it's greater than, so I'm going to fail to reject the null, okay? Fail to reject. The counts are as the company claims, as M&M's, M&M Mars claims. So our counts are not that, they're not so surprisingly different. All right, so move on to the next page of our notes here. And it actually looks like that is it. And the wonderful thing is there's no homework. So the next thing, we are going to have notes on day 32, more goodness of fit tests. So that's it.